Ever wondered what you, the air you're breathing, and a solid gold bar all have in common? Well, the answer is atoms. But if everything is made of the same basic building blocks, why is everything so incredibly different? So, in this explainer, we're going to dive deep and unpack the atom's blueprint to figure out what really makes each element tick.
First up, we'll kick things off with a little puzzle about two very different metals. Then, we'll peek inside the atom to meet the particles that live there. After that, we'll learn how to read an atom's unique ID number and explore some of its alternate versions. And finally, we'll reveal the one thing that's really running the whole show.
All right, let's get started with that puzzle. It's a classic identity problem that really gets to the core of what chemistry is all about.
On one hand, you've got gold. It's shiny, it's yellow, and it's super unreactive. On the other hand, you have iron. It's strong, kind of silvery, but it'll rust if you just look at it wrong. The weird thing is, fundamentally, they're both just huge piles of atoms. I mean, an atom is the smallest possible piece of something you can have. If you could take a chunk of gold and just keep cutting it in half, again and again, the smallest possible particle you could end up with that's still gold is one single gold atom.
So this brings us to the big question, right? If gold and iron are both built from the same fundamental stuff, what is it about a gold atom that makes it act so differently from an iron atom? Well, to find the answer, we have to look inside.
To solve our mystery, we need to zoom in. I mean, way, way in. It's time to meet the subatomic particles that build every single atom in the universe. So, at its most basic, an atom has a two-part structure. Right in the middle, you've got the nucleus. It's this super dense central core. And then, whizzing around that core, you have the electrons, which hang out in these specific energy levels we call shells. It's kind of like a tiny little solar system.
The easiest way to remember these guys is to give them personalities. So inside the nucleus, we have the proton. Think of it as the positive one, the boss, right in the center of everything. Hanging out with it is the neutron. The neutron is neutral, has no charge. It's like the chill friend just keeping the nucleus stable. And then there's the electron. It's negative, super energetic, and it's always flying around on the outside.
Now here are their official stats. Look at the charges. Proton is +1, electron is -1, and the neutron is 0. This is key. In a neutral atom, the number of positive protons is always perfectly balanced by the number of negative electrons. Now check out the mass. Protons and neutrons are the heavyweights, each with a relative mass of 1. The electron, it's incredibly light. I mean, almost 2,000 times smaller. That means pretty much all of an atom's mass is crammed into that teeny tiny nucleus. And to really get your head around the scale of an atom, just imagine this for a second. If you could blow up the nucleus to the size of a basketball, the closest electron would be orbiting it about 5 kilometers, or 3 miles away. That's just wild. It means an atom is almost completely empty space.
Okay, so we know who the players are. Now let's see how we use them to give every single atom a unique ID number. And trust me, it's way simpler than it sounds.
You really only need to know two numbers. First, and this is the most important one, is the proton number. We also call it the atomic number, and its symbol is Z. This number is everything. It's the number of protons, and it is the only thing that decides what element an atom is. If it has 6 protons, it's carbon, always. If it's got 79, it's gold, period. The second one is the nucleon number, or mass number, symbol A. This is just the total count of the heavy stuff in the nucleus, your protons plus your neutrons.
And we write all this down in a standard format, a kind of cheat sheet called nuclide notation. You have the symbol for the element, we'll just call it X. The big number, the mass number A, goes on top, and the proton number Z goes on the bottom. With just these two numbers, we can figure out the entire recipe for that atom.
Okay, let's try it with a real example. Let's crack the code for tungsten 184. So the top number, A, is 184. The bottom number, Z, is 74. Right away, we know it has 74 protons. To find the neutrons, we just do a little subtraction, A minus Z. So 184 minus 74 gives us 110 neutrons. And because atoms start out neutral, the number of negative electrons has to match the number of positive protons. So 74 protons means 74 electrons. See? Simple as that.
So, what happens if we start changing these numbers? This is where we get some really cool variations of our standard atom. Let's talk about ions and isotopes.
Okay, so the most important rule here is that the number of protons never changes for an element. If you change the protons, you get a totally new element. Got it? So an ion is what you get when an atom gains or loses electrons. It gets an overall electrical charge. An isotope is what you get when you change the number of neutrons. It's still the same element, because the proton number is the same. It just has a different mass.
Hydrogen is the perfect example. Every single one of these has exactly one proton. That's why they are all hydrogen. But look closely. Regular hydrogen has 0 neutrons. This one, deuterium, has 1 neutron. And this last one, tritium, has 2. They're all still hydrogen, they just have different weights. That's what isotopes are.
All right, we've cracked the atom's code, we've met its alternate versions, but we still haven't fully solved our original mystery. Why are gold and iron so different? Well, the secret has been hiding on the outside this whole time.
It all comes down to the electrons. Specifically, how those electrons are arranged in their shells. This arrangement is called the electronic configuration, and it is the #1 thing that determines how an atom is going to behave, its entire chemical personality.
Let's try to build an atom. The very first electron shell, the one closest to the nucleus, is really small. It can only hold a maximum of 2 electrons. You can see that here with helium. It has 2 protons, so it has 2 electrons, and they fit perfectly in that first shell. That makes the shell full, which makes helium super stable and unreactive. It's happy on its own.
Now let's look at lithium. It has 3 electrons, so the first 2 fill up that inner shell. But what about the third one? Well, it can't squeeze in there. It's forced to start a whole new shell, a second shell further out. This single electron, all alone in the outermost shell, has a special name. It's called a valence electron, and that term is super important.
Let's jump ahead to sodium. Sodium has 11 electrons, so its configuration goes 2 electrons in the first shell, then the second shell fills up with its maximum of 8, and that lonely 11th electron, it has to start a third shell all by itself. So just like lithium, sodium also has 1 single valence electron. That's not a coincidence.
And this is it. This is the answer. The number of electrons in that outermost shell, the number of valence electrons, is what dictates an element's chemical properties. Gold and iron have a different number of protons, which means they have a different number of electrons, and a totally different number of valence electrons. It's those outermost electrons that interact with the rest of the world, and that is why gold is gold and iron is iron.
So we figured it out. An atom's identity comes from its protons, but its personality comes from its electrons. And that leads to the next big question, doesn't it? What happens when those outer electron shells get close enough to meet? What happens when they decide to share or even steal those all-important valence electrons? Well, that's the story of chemical bonding, and that's for another explainer. Thanks for joining us.